if we know how much work it takes to stretch a perfectly elastic spring 6 centimeters from its equilibrium position, can we find the spring constant? And can we find how much work we need to stretch it an additional 6 centimeters? I would say that we can, and we'll do it using our understanding of work. First, we'll call the equilibrium position. That's where the spring is relaxed. We'll call that x equals 0. So it's not stretched, it's not compressed. We know from integrating the force of a spring that the work it takes to stretch a spring, which given by the problem statement is 0.54 joules, is equal to 1/2 k times xb squared minus xa squared. That's stretching it from xa to xb. When I actually derived that, I found the work done by the spring, and that was a negative. So that means that the work we have to put in is the opposite of that. It's a positive. We're starting from some initial position that's equilibrium position, so we'll call that xa 0. And we'll call xb that second 6 centimeters worth of stretching, or 0.06 meters. We can now plug in the things we know and solve for the thing we don't know. Normally I solve this stuff algebraically first and then plug stuff in at the end. Here I'll plug in some numbers, if just to demonstrate that this is a perfectly valid way of doing it. I just prefer doing more algebra and less having numbers in my algebra, more symbols. The xb was 0.06 meters. The xa was 0. We can now solve this for the unknown k by multiplying 0.6 by itself, dividing by 2, and then dividing by whatever the result we get on both sides to end up with a k value of 300 newtons per meter. That's a spring constant, which tells you how stiff the spring is. So to stretch the spring out a meter, you need to put in 300 newtons. In practice, if your spring's not long enough and you try and stretch it a meter, it's going to destroy the spring. So this is only valid during the point where you're stretching and compressing the spring and not doing plastic deformation. It's elastic deformation where it's restoring to its original length in between. Unit-wise, you might wonder how that worked out unit-wise. Well, let me give you a little bit of a peek behind the curtain. We end up with twice 0.54 joules over the 0.06 meters squared. And in doing the unit conversions here, we end up with joules per meter squared. And 1 joule is equal to 1 Newton meter. The joules end up canceling. You're left with Newton meters per meter squared, which ends up with a Newton per meter. All right, units are good. We can now say how much work does it take to stretch it an additional 6 centimeters. In this case, we'll say the work it takes is that same thing, 1/2 k xb squared minus xa squared, where we're starting from an xa of 6 centimeters from the previous thing, or 0.06 meters. And we're going to a new stretched position of 12 centimeters, or 0.12 meters. You plug that stuff in, and you get 1.62 joules worth of additional work.